Yes, class. Am I audible to all of you? Austin, Faiza, Tarif, Shahid.
Yes.
All. So in the last class, we had started with electric potential and capacitance. So see, we had seen what is the concept of electric potential. Basically, it's just electric field in scalar form. This is what we had seen. And again, the source charge was present, the test charge was present. And in a similar manner, we had seen, we had obtained the formula for potential due to a point charge also. So one of the definitions of electric potential was that if we take charge as 1 coulomb, right? So potential becomes equal to work done. So in that case, our definition, what does our definition becomes? It means that electric potential is basically the work done in carrying unit positive test charge from infinity to a particular point against electric field without any acceleration. This is the definition of potential which we had seen. Now, apart from this class, one of the, I think we had stopped at this point only, though, where we had seen the formula for electric potential due to a point charge, right? So this derivation can come in your exam, which we discussed. So see, 1 over 4 pi epsilon naught r into q, that is kq by r, you can remember kq by r, that is, this is simply what is meant by this. K means 1 over 4 pi epsilon naught, whose value is 9 into 10 to the power 9. 1 over 4 pi epsilon naught, 9 into 10 to the power 9. This is the value of this K. So electric force becomes kq square by r square, electric field becomes kq by r square, electric potential becomes kq by r. This much we had completed. Now see, class, if this is electric potential due to just a single charge we had seen, right? This is just due to a single charge. If one charge is present, what will be the potential because of that charge? That we had seen. Suppose if I tell you more than a single charge is present, the way we had seen it in case of electric field, if more than a single charge is present, then how will you determine? So see, in that case, when more than a single charge is present, we'll apply superposition principle. But in electric field, how will the superposition principle be different in this case from the case which you have studied in electric field? Is, see, in this case, your potential is a scalar quantity. So you don't need to take all the parallelogram law and calculate the angle and find out the resultant. Here you just have to algebraically add all these, right? So if suppose these many charges are given, at this particular point I want to find out. So see, due to this charge also, this charge Q1, potential will be K Q1 by R1. Due to this charge, potential will be K Q2 by R2. Due to nth, suppose we have n number of, so due to this nth will be Vn will be K n divided by Rn. Right, this is the formula of potential we'll see for every individual charge. So if I want to find out what is the net charge at the point, now this is not a property of a this is a electric potential is a property of a single charge, but if you want to find out the net resultant potential at a particular point, and n number of charges are given. This n can be any value. It can be 2 charges which are present, 3 charges, 4 charges, 100 charges, infinite number of charges can also be present over here. So we have individual values of charges. So since we had discussed in the last class, this is not a vector quantity, it's just a scalar quantity. You just need to add all of this. If potential is positive, add it. If it is negative, minus V, however it is, you just have to algebraically add it. No vector signs over here. V3 plus up till Vn. This is what you have to use in here. That's it. So for a system of n interacting point charges, electric point at a point, electric potential at a point, this is the algebraic sum of potential due to individual charges. All right. So whatever is the electric potential due to individual charges is given by net formula. Just simply adding it. One more thing, class. In the last class, we had seen the formula for work done, right? If suppose, just revising it, if this is point A and here I have point B, I'm moving from A to B. So now remember the formula which we did, change in potential, this is equal to work done divided by the charge. So when I say change in potential, when I say this change in potential, this means final point minus initial point. So this is actual change in work done. So if I want to find out work done rather than finding out potential, so work done will be change in potential multiplied by charge. So charge will be as it is, but change in potential will be similarly.
Okay, repeat this.
Final, see, if we have 2 points, right? One is initial point, one is the final point. And I am moving one charge from this particular A point to this particular B point. Fine, from A to B, I am shifting the charge. So change in potential that will come in this charge, change in potential will be final potential minus initial potential. Is my voice still breaking? Just wait, just wait. Yes, class. See, now I'm repeating this part. If my voice still breaks, please just let me know. I think now the internet is better. I'm saying if I have two charges, right? I have one single charge and I have 2 points. So I'm shifting this particular charge from A to this point B. A and B are present on the screen. You can see. So what will be the potential difference? Final minus initial. That's how we write now. How do we write the potential difference? Final potential difference minus initial. So this is going to be VB minus VA. That is the potential difference. And from this formula, this particular formula, which we had seen earlier in the last class, work done will be written as charge multiplied by change in potential. So what will be change in potential? If you have 2 points, write down the change in potential properly as VB minus VA, like this, because two potentials can be given to you. And one more thing, class. Apart from this, this point can be useful for the numericals. If instead of work done by external field, work done by electric field is asked to you. Just in case work done by electric field. This is asked to you. So whatever is the work done by the external field, right? Whatever is the work done by external field, minus of it will be the work done by electric field. Minus of work done by electric field. So whatever answer you will get here, if you have to answer it for electric field, just put a negative sign. This type of question, a question based upon this whole concept, we'll do it just right. But before that, just write down the superposition principle that if you have potential for n number of charges, how will you solve it? Fine, so note that down first, then we'll solve a question. Am I audible now, Faiza? Is it fine? Am I audible, class?
Yes, ma'am.
Yes, sir.
See class, in this question you have, again, 2 points are given. Now work done you have to calculate in by the external force, not electric field, by the external force in carrying electron from A to B. So A point is given at 10 volt, B is given minus 20 volt. So work done in carrying a charge from A point to B point. So see, what will be the change in potential? Change in potential will be the same. Final minus initial, that is VB minus VA. So VB minus VA, this is the change in potential. Fine. Now, see, this is how.
Ma'am,
Yes.
what is the difference between external force and electric field?
See, electric field is present. Electric field is itself a quantity that is causing. Now what happens? Under the influence of electric field also motion occurs. Under the influence of electric field, force occurs. Due to that force, acceleration occurs. And due to that acceleration, the charge moves and a specific velocity is also there. We are not studying that part because we are currently dealing with electrostatics. That's why we are just neglecting that portion. Otherwise, in reality, if electric field is present, because of electric field, electric force will also be there. F is equal to QE. We have seen that formula. And if force is there, F is equal to ma, Newton's law. Acceleration will be there. Entire motion will be in your, entire system will be in motion. So what will happen? In that case, electric field will also be generating the charge to move from one particular point to another particular point. And because of that, what will happen? When the charge will move, we'll get two different potentials. One is work done by external force. Suppose I am the external force. I am deliberately moving charge from A to B. Or let's say some gravitation, due to gravitational force, A or B, the charge is moving from A to B. So any external force that is not a part of your system. When I say system, right now for me, the system is the A point and B point. This limited boundary, this is my system right now. Now, when I say any other force apart from this, any force, frictional force, gravitational force, electric force, any sort of force, it can be electric force as well, that allows the charge to move within this, that becomes external force for us. So when we say electric field, when we say external force, this is the difference. When you are specifically referring to electric field, and because of electric field the charge is moving and work done is occurring, then in that case we say this is the work done by electric field. If simply the two charges are moving and one force out of their system, when I say system, it means just a system of these two charges. Any external force is acting and then the charge is moving because of that force, and work done is getting generated, and then we are having the potential that is work done by external force. Fine. So see, at this particular point, VA charge is VB minus VA. This is equal to the work done by external force, right? Now see, charge is given, electron is given. So see, if charge is not mentioned, it means electronic charge. So in the first class of electrostatics only, we had discussed that electric charge is, what is the value of electronic charge?
1.6 into
1.6 into 10 to the power minus 19 coulombs, right? Because see class, please remember, all those who have still not remembered the value of electronic charge, no, please remember it, because I have told you in your, till your last lesson, even still semiconductors, entirely this electronic charge we'll be using it. So electronic charge we'll put VB, this is minus 20. Here we have minus 10. This is the work done by external force. So what will be the work done by the external force? Charge, that is 1.6 into 10 to the power minus 19. And see, this is electron. And when we talk about electrons are negatively charged particle. So we have to put a negative sign also. This is the charge. No, I'm not taking the magnitude right now. What did we learn? We don't have to take the magnitude only when we talk about scalar quantities. Potential is also a scalar quantity. Charge is also a scalar quantity. Work done is also a scalar quantity. All the three quantities are scalar. So I'll put the sign multiplied by, here I get minus 30. So right now I'm getting a positive work done 4.3 into 10 to the power minus 18. I think this will become 18 joules. Please just check. This will become minus 18 joules. Now see, if suppose in this question, potential is asked to me, or the net difference potential, that would be only this minus 30 volt. Fine. Charge is this only if potential is asked, then this is just the answer. When work done by external field is asked, we mention one more step. Suppose here there's a modification, let's say. Suppose this I give you. Calculate work done by electric field in carrying 2 coulomb from A to B. Now, this is not work done by external force. This is work done by electric field. Electric field is making the charge move because of its presence. Now, see, here also we'll put VB minus VA. That is the change in potential difference multiplied by charge will be work done by external field, not electric field. So what will be the formula? 15 minus 5, charge is also given as 2, is work done by external. So work done by external force, this becomes 10 into 2, that is 20 joules. So 20 joules is, in this question, I am getting work done by external field. Now what is being asked? Calculate work done by electric field in carrying charge of 2 coulomb from A to B. Fine. So if it is then this case, then work done by electric field, this will be done by external force. So work done by electric field, this becomes minus 2. This is the difference between both the questions. In this question, it was just work done by external force, so simple. Work done is charge into change in potential. If it is work done by electric field, just put a negative sign. Fine. Note down these two questions. See, all those who have completed this writing part, try with this question, question 3, and send me your answers in the chat box. Potential at point O, potential at point T, and work done in carrying proton from O to E. At least note it down, try it by yourself, then I'll discuss this. Maria, this question.
Ma'am, the second one. Okay, ma'am, done.
Ma, can you just scroll up? I was just connected. Yes, ma'am.
Look, class, I'm discussing this. 4 charges are given to you. This is a square with side A, B, C, D. These are the 4 vertices of the square. Now, see, at A point plus E is given, at B point minus E is given, at C point plus 2E is given, and at D point minus 2E is given. Fine. Now it says that calculate potential at point O. So when I'm talking about point O, forget all these red lines. Fine, forget all these red lines, because when you are focusing on point O, this should be just the figure for you. A square plus E here, minus E here, 2E here, and minus 2. That's it. Separation is A among all of these. All right. Now, potential at point O, we have to find out. Look, class, one thing. This particular point is needed, right? If I say because of this D point, I want to find out the potential at this point O. So for every potential, we need the separation from the surface, right? From the point of calculation to the point where charge is located, we need to have the separation. That is what we take as R, no, in our formula. So this is suppose our R. So for every charge, we have to find this, and for square, this will be same for all. So what will we do? See, if we have this, let's say this is the triangle, this is A, this is A. So automatically this becomes root 2A. right? If you apply Pythagoras theorem, this becomes root 2a. And if your AC is root 2a, then your AO means half of it, right?
A by
Yes, exactly, A by root 2. So entire AO or this BO or this CO or this portion DO, this will be equal to A by root. This is the separation. At least now we have R for this. Clear? Now you have charge, you have R. What is the generalized formula? V is equal to KQ by R. This is how we calculate for a point charge. Now you know what is the value of K. Charges are also given, and separation of all the charges from the point of calculation is also given. Now we can calculate this. See, VA, potential due to A point, will be what? General formula is KQ by R. So A will be K, charge at A point is E. So E, R separation is same for all, that is A by root 2. What will be VB? VB will be C. This is point of calculation, this is B. So K, what is charge? Minus E. So you'll put minus E by R, that is A by root. Fine. Similarly, see, if we have to find out VC. Now, what is the charge present for VC? At this point, we have plus 2E. So that becomes K, 2E, KQ divided by RB, right? So R will become A by root 2. And what will be VD? What is the charge that is present? Minus 2E. This is the charge that is present. So this becomes K minus 2E by A by root 2. Fine. Now see, what will be the net potential? What have we just studied today? If n number of charges are given, more than a single charge is given, calculate individual charge the way you have been calculating, and at the end algebraically add them. So V net at point O, this will be VA plus VB plus
Zero.
VC plus 0. Exactly. Because this will be KE by A by root 2 minus KE A by root 2 plus 2KE A by root 2 minus 2KE A by root 2. So all gets cancelled. This gets cancelled. This subtracts this. So net potential at O point is C. This is the answer for the first. Yes. Potential at point O. Fine. Now we have to find out potential at point E. So I think now at least you can try for E. At least you have the idea. You have to find out the potential at this particular point. So separation from this charge is required. Separation from this charge is required. Separation from this charge, separation from this charge. And then put it into the formula KQ by R, add it, you will get it. Note it till here. Question, I think some of you have not written the question as well, no? Write down the first part, I'll discuss the second part then. But at least those who have written or those who have understood after writing, at least try with the second part. Because third part is very easy. Whatever will be the answer, that will be just one or two more steps. Third part is very easy. Just calculate second part, similar to first part with just some modifications. See, VC and VD. See, what is the general formula? K Q by R. So this is K. Charge is given at C point 2E. So Q. And what is the separation from the charge to the point O? A by root 2, which we have calculated. So A by root 2. So K Q by R. Same is case for VD, but in VD we have the charge as minus Q, minus 2E. So K Q by A by root 2, that is separation, like this. Next question also, next part also you have to solve in this manner only. See, this triangle, if I want to find out the net resultant potential at this particular point. See class, what I require, K, Q and R for putting in this formula. K is a constant that will remain constant. Charges are already given. Just separation is not given to me, no. Just the separations are unknown. So see, in that case, this is given, this separation is given from this charge. This is A by 2. This is given in the question. This is also given. From these two charges, A and D, no separation is given, right? So this we can find out using Pythagoras theorem. See, for the second part, suppose this was the portion. I'm drawing this just separately. A was here, E is the point here. A, B, B, E. This was given. This was A by 2. This was A. This is only missing, no? AE. So we can find out AE using Pythagoras theorem. So this becomes A square by A by 2 whole square using our Pythagoras theorem. So that becomes 4A square plus A square divided by 4 under root. So that becomes root 5A square by 4, which is A root 5 by 2. So this separation we have A root 5 by 2. So also, so this separation, which was DE, this will also become A5 root 2 by 2. And this point, this is also A by 2. So we have separation from all the charges. A was plus E, B is minus E. This point C is plus 2E, D point is minus 2. So we have all the charges. See, charges are also present, separations are also present. What do we have to do? We just have to find out the net potential. So see, and for these two, we already have A by 2. So VA here, this will be equal to, see, this is the charge. So KQ, we put KQ by R. So KQ will become E. And what is the separation? How do we calculate this separation? Calculate the separation from the point at which you want to find out the potential. Like I want to find out at this particular point E right now. So separation of E to the charge. What is E? This capital E, separation to the charge is E. So this is A root 5 by, fine, this is VA. Now VB, same thing. K, now charge is minus E here. And what is the separation between point of calculation and charge? This is A by 2. There is the separation from B point and E. This becomes A by 2. VC is this. So VC will become K. What is the charge? 2E. And what is the separation between both the points? A by, right? Lastly, this point is left, VD. So KQ by R. This is K. What is the charge given here? Multiplied by minus 2. And what is the separation between these two portions? We have calculated A root 5 by 2. So here our answer won't be 0, because see, now when we'll add all these quantities for the net potential at this becomes, let us shift this 2 upwards, because here we have to solve. So 2 KE by A root 5. From here we have minus 2 KE by A. From here we have plus 4 KE by A. How am I calculating? I'm just transferring this 2 to the numerator, because this new is in the denominator's denominator. So this will go up. That's what I'm doing. So when this 2 goes up, 2 into 2, this becomes 4. That's what I've written. Minus, this becomes 4 KE A by root 5. So one thing we can do, we can at least take some things we can take common. So from here, 2 KE by A is common everywhere, right? So at this particular point, if we take 2ke by a common, so what is left here? 2ke by a. 1 by root 5 is left. 2ke, from here minus 1 is only left. From here only 2 is left. From here minus 2 by root 5 is left. Right. Now see, you have your answer. So see, this becomes 2ke by a. 1 minus 2 by root 5. That becomes minus 1 by root 5. And 2 minus 1 becomes 1. So this is the answer. VE is 2ke 1 minus 1 by 2. This is the potential at E point. Now look class, third part is asked work done in carrying proton from point O to point E. From this particular point O to this particular point E. So how do we calculate the work done? In any case, we have to find out the work done. Work done's formula is, just now we have studied before this part, before this question, we were studying that final potential minus initial. So if it is going from O to E, potential at E minus potential at O. Now C class, what is the charge given? It is saying carrying a proton. So proton has the same charge as electron, electronic charge only. So we'll put 1.6 into 10 to the power minus 19 coulombs. This is the charge that is given. And what is VE? VE we have calculated right now. That is 2ke by a 1 minus 1 by root 5 minus VO in the first part. What was our potential? All got cancelled. It was 0, right? So work done will be just the charge multiplied. So let's write this as E only, because here we don't have to find out the magnitude. So E, instead of this, I'll write this as, this is E only, protonic charge. So this becomes 2ke square. This E gets multiplied with this. 1 minus 1 by root 5 is left. This much is the work done. This is the answer to the third part. Tell me, this question is clear to you? All of you?
Yes.
All right. Note it down. Note down the second and the third part. First, you have already written it.
Ma'am,
Yes, Madhya, say.
ma'am, can you please scroll up to the first part? I have a question. Ma'am, here when we took out the length of AO, like the length of this AC is root 2A, right? So when we're taking out the length of AO, like won't it be root 2A by 2?
Yes, see, that is root 2A by 2 only, root 2A by 2.
Okay, we
But
have simplified it.
yes, yes, we have rationalized.
Alright,
All right.
alright.
Done? Now, dipole we had studied in electrostatics when we were discussing dipole. So what was dipole? Dipole meant that two charges are present. Both the charges will have the same magnitude and opposite signs, right? If suppose I have plus 2 coulomb at one place, so I should have minus 2 coulomb with a certain separation from it. That would be called as a dipole. When two monopoles of opposite signs but same magnitude are separated by a small separation, we call that combination as a dipole, right? So this we had studied dipole moment also. We had seen charge was multiplied charge of one magnitude of one of the charges multiplied by separation of both the charges. So that was dipole moment we had seen. Now see, that was related to electric field, which we had seen. Remember, after this, P is equal to Q into 2A, we had seen the formula for electric field at axial point and equatorial point. Now the same thing comes in potential. We have to find out the potential at axial point and at equatorial point. But see the difference that comes here, no? Here, what we'll do, first we'll derive the formula, general formula. If it's not on axial point, if it's not on equatorial point, it is just on a situated on a random angle. The point is situated at a random angle from the dipole. Now, after we have obtained the formula, general formula for potential due to a dipole, then we'll put in the values for axial and equatorial. So this is a different case which we had studied in electric field. In electric field, we separately find out, no, electric field for axial, electric field for equatorial, like this. Potential, we'll find out the common general potential and then we'll substitute in the values. See, you'll understand. Dipole is what? Suppose I have plus Q. This is separated from minus Q. Find separation between them is 2A. I have been given a random point. Let's say this is the random point P. Fine. So this P will be separated. See, this P has a separation from this charge as well. This P has a separation from this point as well, right? Let's say this is R1, this is R3. This is A point, this is B point. This at the center is O point. If O is your center, at the center, then this part will be A.
Ma'am,
Yes.
this should be potential at point P, right?
Potential at point P. Yes, yes. Potential at point P. No, don't look at this. I'll tell you. This is something else. This just focus on the diagram. I'll come to that part. So right now we'll find out potential on P due to A or due to B, like this. Potential at point P. I'll just change it. Now, see. And also, let's say, let me just extend this line. Let me extend this, fine. Why have I extended this line? Because I need some construction. This is the derivation. That's why this is a little in detail. It's a little lengthy. Potential at a particular point when we have to find out at a particular point A, B, C, D, O, P, wherever point we have to find out. Now, see, so just go step by step, you will understand. After that, you just have to remember the formula. So this is it. Now I have to do some construction. That construction was basically, let me drop perpendicular from both the charges. Fine, I'm dropping perpendicular from both the charges. So from here, let's say this becomes, this is this AB, this becomes C, this is D. These are perpendiculars that I have dropped on the surface. Fine. So what I have dropped? From here, B I have dropped T, and from A I have dropped C. These are perpendiculars. And they are subtending some angle also, that is theta. This is the diagram. Now, if I want to find out the net potential in general, so as rightly I was saying, this will be when I'm calculating potential at point P. When I'm calculating the potential at this particular point P. So potential, it would be due to A charge as well as B charge. So KQ by R is our general formula. So K, what is the first charge? Q. What is the separation? Separation I have taken right now as R1. Second, K charges minus Q by R2. So KQ by R1 minus KQ by R2. One thing that we can do is we can take KQ common and we can substitute 1 by R1 and 1 by R2 like this. Now class, the major task. R1 and R2 are not given to us. We just have the charges with their separation. That is the dipole. We do not have this R1 and R2. This I have drawn it myself for derivation purpose. So what I have to, if I have done such thing, then I have to substitute the actual values what R1 and R2 contain. Now see, in these triangles, if you look, these small triangles that have been constructed, what is cos theta? cos theta is basically base by hypotenuse, right? So in triangle, if you look at this triangle ACO, this is point O, ACO. In triangle ACO, if we write down the value of cos theta, that becomes OC divided by AO, right? Base by hypotenuse in this AOC triangle. So that becomes OC divided by AO. So what is OC? What will be OC? OC will be AO cos theta. And what is AO? Entire separation between the two charges was 2A. So till the middle point separation will become A. And that's what.
Where is O?
Yes.
Where is O here? O point.
O point is this point. This particular point. This is point. Middle point.
Okay.
Right? So entire is AB separation is 2A. If I want to find out the separation from this middle portion, that becomes A. That's why I've already marked this as A already. So this means OC becomes A cos theta. Now class, look here. When we are solving this, no, in reality, why have I taken this perpendicular? Because this point PB line and this line PA, they were not equal. I wanted somewhat near equal line, then only some calculations could be made, right? That's why these perpendiculars are dropped. Now look class, PB is very shorter, is shorter as compared to PA, right? This PB one is shorter, this one is lengthy. But if you look at PC and PA, both are almost equal, right? PA and PC both are almost same. So PA is almost equal to PC. What is PA? This entire, this is PA, right? This is equal to almost, we can say PC. Now class, look at this. PC is this line. PC is made up of PO plus OC. That makes PC, right? PO till the point O, PO plus this additional perpendicular part OC that we have drawn OC. So entire becomes PC. So how can I write this PC? I can write this as PO plus OC, right? PA becomes, what is PO? This is PO. This is PO. Let's write the value of PO. So let's say this is R. Let's say this value is R. This is R1, this is R, this is R2. We'll substitute it later. So what will PO become? PO, let's say this is R plus OC. OC also we have calculated A cos theta, right? Do we know the value of PA? Yes, we know the value of PA, that is R1. R1 is equal to R plus A cos theta. Why have I taken this point as R? Look here. Why have I taken this particular point as R? R1 and R2 are unknown. Remember when we were doing the derivation for electric field at equatorial point or electric field at axial point, if the dipoles were given like this, plus Q minus Q were at certain separation, point P was here. We used to calculate from the center to the point of calculation as R. Remember in the formula. So R basically represents what? R basically represents the separation of center of dipole and point of calculation, the way we were doing in electric field. Or remember when we were having potential questions, so this was chosen as R. So same thing is happening here as well. Here also, this particular point, this is chosen as R because there is a separation from center of dipole to the point of calculation. Center of dipole to the point of calculation. So this is the R that we get in the formula. No, remember in electric field also we had Kp by R cube minus 2 Kp by R cube, all these formula we had. So same thing. Fine. So we have the value of R1 with us. Now a similar thing will happen. Now just it would be repeating itself. If you focus in this triangle, this is OBD triangle. So same thing will happen in OBD triangle also. Look, if this is the triangle, in triangle OBD, It was D, no? OBDS. So same thing, cos theta, we'll find out that will become perpendicular is OB, and perpendicular here is BD. Perpendicular is BD by OB, BD by OB. This becomes the way in the previous, from the first part. See, this was from this OC by O. Yes, exactly. So in this also we'll use the same concept. This is the triangle now. I'm not focusing on ACO. Okay, this was the confusion. This is ACO. I am focusing on this now. That is over. R1's value I have got. See, R1's value is obtained. R1 was missing. Now I'm trying to find out the value of R2. Look here. Perpendicular.
Ma'am, in question they will not directly give R1 and R2.
No, R1 and R2 won't be there anywhere. You won't be even needing it. This is just for the derivation purpose, because in your 12 board exam, derivations are asked. That's why. When we'll reach out the answer, you will just be having small r. So in the question, small r will be given to you. R1 and R2 won't be there. That's why we are also trying to eliminate it. Otherwise, this would have been our answer. This would have been our answer. All right. So similarly, in this triangle, this becomes OB divided by, what was this? This becomes OD by O. This becomes OD by OB. Fine. So OD from this becomes OB cos theta. Again, OB is the separation. AB was entire. OB becomes half of it. That is A. This is also A cos theta. This is also. Now in this, the shorter ones, PD and PB, they are almost equal because PO is lengthy. So PD and PB, they are almost equal. So what can we do? We can write entire PD. This part, this is PB, right? This is PB. PB is almost equal to PD. So what can we write PD? Entire PO, this PO. From this PO, if I subtract OD, what will be left? PD will be left, right? Look at the figure. In this figure, if you look, this is entire PO, right? From PO, if I subtract OD, what will be left? PD will be left. So PD can be written as PO minus OD. Got it, class? PO minus OD. This is what can be written. PB is R2, PO is R, and minus OD is A cos theta. That's it. Values of R1 and R2 are here with us. This is what was known. That's why we had made the calculations also. Now just substitute in the values of R1. This is, let's say this is the first equation. This is the second equation. And this is the third equation. So put 3 and 2 in 1, that which was missing. So your potential, this becomes understood. Now we are just substituting the values. KQ was given. Capital Q, I have taken a small q. Small q. So KQ 1 by. This becomes R plus A cos theta minus R minus A cos theta. We just have to now this is simple algebraic solving. How do we solve algebra? Now see, V is equal to. What can you do? You can take the LCM and solve it. So this is R minus A cos theta divided by R plus A cos theta. So see, this KQ, this is taken common, right? I have taken this KQ common. This was already taken common initially. This is the same thing. Now we have just put in the values, right? This is one quantity. This is another quantity. We just have to now solve them and take out their LCM. All right. So now this becomes, this is R minus A cos theta minus R plus A cos theta divided by R minus A cos theta into R plus A cos theta. Fine. This is it. Now look here. If we open up the brackets, that is, this is A minus B So in the denominator is like, you must have heard of this identity, a plus b into a minus b. Yes, you must have heard, that is a square minus b square. So here also, no, r is behaving like a and a cos theta is behaving like b. So a minus a square minus b square, right? So a minus b square, the way we write. So same thing is here also, a minus a square minus b square. This way we'll be writing it. Now look here. So v becomes kq. In the denominator you have r square minus a cos square theta. Why? Because a square minus b square is given. Now see, if we open up the identity, here we have, why we have substituted this? That's what I was saying. See, a plus b into a minus b. This is a square minus b square. Fine, a square minus b square. This is it. Now see, when we take r as a, this I have taken r as a and I have taken b as a cos theta. Fine, I have taken this. Yes, this was the case. Understood? So this becomes a square minus b square. Just look, okay, take a minute, just say. This portion, this is just your mathematical identity, which you must have studied earlier in your earlier classes. You want to write it, do one thing, class. If you are having confusion, no, because we were just about to reach the end only, do one thing. Do not even write this part till just here, till these equations first noted down. And whoever is having confusion, get it clear till here, then we'll write out the concluding formula. Write down till here at least. Yes, Faiza, I'll send. And class, I think you had your chemistry test, no, on Friday. So now will be physics test.
Yes, sir. This Friday.
Yes. Just write it till here quickly. Just here.
I can just a little bit scroll. Yes, ma'am.
So till now, what did we do? We had the dipole, we took a point P, and from the point P, from both the point charges, Q plus Q and minus Q, we calculated the potential. So in our potential, we were getting 1 by R1 and 1 by R2. So R1 and R2 we have found. Yes. Now what we have to do, this was what was required by us. Now we just have to substitute in the values of R1 and R2. So R1 is R plus A cos theta. R2 is R minus A cos theta. How did we get it? We just got it from the geometry by using cos theta. Using trigonometry, we got the values of R1 and R2. Now we are just substituting it. So see here also V is equal to KQ. So now this is clear, right? A square minus B square till here we have used. So this, as I was saying, now this becomes R square minus A square cos square theta. Fine, this becomes A square minus cos square theta. So this becomes R minus A cos theta minus R minus A cos theta. So R gets cancelled. What is left? KQ minus 2A cos theta. Yes, 2A cos theta by R square minus A square cos square theta. Now class, just
Q,
one thing.
yeah,
Q
into 2A will be P, right?
Yes, exactly. That is dipole. So charge multiplied by this 2A. Just eliminate this negative. Let me write this negative sign outside. So this becomes, what is this quantity? Q multiplied by 2A. Dipole moment. Right. So at least we have figured it out. What was the dipole moment? So now see, we have got the formula for dipole moment. The formula, this becomes V is equal to K. I'm not writing down the negative sign. I'll tell you right now. This is K. This becomes P. So Kp, this is cos theta divided by R square minus A square cos square theta. This is the formula for dipole. Now, regarding this negative sign totally depends upon the dipole's orientation. If I take dipole as plus Q here and minus Q here, then I'll be getting a negative in my answer, the way I'm getting here. If I rotate this, if I take minus Q here plus Q here, then I'll get a positive answer. So that doesn't change the answer. We have the formula. You just focus on this formula. Depending upon the orientation, directly you will get the answer as positive, negative, because potential is a scalar quantity. So if it is negative, directly in your answer, you will get negative sign. So in this is the actual formula, Kp cos theta by r square minus a square cos square theta. Depending upon the orientation, you'll get plus minus. So this is just the magnitude, main thing that we have to focus on. Regarding ideal dipole approximation, equatorial axial, that we'll see in the next class. But see, currently what it now, after writing, I hope now this is clear to you, whatever you have written, whatever was the confusion regarding this identity some students were having. Now I think till here, this step, if this is clear, no, how you have found the values of R1 and R2. Now after this, you were just substituting it and getting the values of potential. So this is the actual formula. We'll see some approximations are also there. Values for equatorial and axial also we find out, that we'll see later on. So till where all of you have, first will be, now this is clear after writing it till here. Clear to all of you?
Yes, ma'am.
Yes.
All right. So from where you want to write? I think this you have written, no? Or somewhere writing this. If this is okay, noted. See, minus a cos theta, minus a cos theta. They won't get cancelled, they'll get added up. So we get minus 2a cos theta. Here we had minus a cos theta. Because of this negative sign, this also became minus a cos theta. So minus a cos theta minus a cos theta becomes minus 2a cos theta. Here we cancelled these because this was plus r and this is minus r. So plus r minus r, that makes it 0. All those who have completed, just text me done in the chat column quickly. So all of you have completed. Anybody who is still writing? So all have completed.